Hi everyone. So in today's video, we're going to be going over a couple more examples of optimization problems. So in yesterday's video, I kind of outlined the general idea and process for solving optimization problems, and we did a couple of examples there. And then today we're going to do a couple of other examples. So the examples we did in yesterday's video were kind of related to graphs. So we had an example where we had defined the distance, the shortest distance from a point on a graph to another point. And then we also did a problem where we were trying to maximize the area of a rectangle below a graph. So today's examples are going to be a little different. They're going to be more like kind of word problems. But the general approach will still be the same. So we're still going to be kind of using these steps as our process for solving them. So the first example we're going to do has to do with fencing. So that's kind of one of the classic questions that you'll see in optimization is building a fence. So this question says a farmer has 2,400 feet of fencing and wants to fence off a rectangular region, bordering a river. So we'll see once we draw a picture that basically that means that we only need 3 sides of fencing because the river is going to form that other barrier. And so the question we're going to answer here is, what are the dimensions of the field or the region with the largest possible area? So we're going to figure out basically, like, given the amount of fencing that we have, so 2,400 feet, what's the biggest area we can build is basically the question. So what are the dimensions of the region with the largest possible area? Okay. So let's start by drawing a picture, and then we'll jump into answering the questions like what is it that we're trying to maximize, and then go from there. So we have in this situation a river, and then we have we're trying to fence in an area, so something like this. This is not going to be like correct from a perspective point of view. But, okay. So here's our river, our fence. And so we're trying to maximize the area inside of here. So we're basically trying to maximize this area. So let's write that down as our kind of first step in this question. So the first step is that we're trying to maximize the area of that green rectangle. Okay, so our next step is going to be to write down a function that represents that area. And so in order to do that, we need to introduce some variables. So it doesn't really matter what variables we use, but maybe let's call this horizontal distance x and these vertical distances y. So because it's a rectangle, these two sides are both the same length, right? So we have y and we have x. So we can start by writing down an area. So the area of a rectangle is always base times height, right? So that would just be x times y. However, as we saw in yesterday's video, generally speaking, in these questions, we need to find a way to express our whatever the function is that we're trying to maximize, we need to express that in terms of only one variable so that we can, do calculus basically. So that's where we have to look back to what the question, some of the details of the question and see how that can help us. So it tells us that we have 2,400 feet of fencing. So what does that mean? That means that basically the length, so when we wrote down this formula, A is equal to X times Y, we're talking about area, but the 2,400 part, that comes from length, right? That's the length of all of these pieces of fence. So based on the question there, if we have a total of 2,400 feet, that means X plus Y, so X plus 2Y is equal to 2,400, right? Because that's the total length of the fencing, is we have this one piece that's length X and two pieces that are length Y. So we can use this to help us basically get rid of one of the variables in our equation. So you could do it either way. I think it probably is a little easier to solve this equation for X than for Y, just so that we don't introduce any we don't have to do any division. So X is going to be equal to 2,400 minus 2Y. So what does that mean? That means that now we're going to replace X with 2,400 minus 2Y, and that will give us then a function that it's going to be a function of Y. But that doesn't matter, right? Like, it doesn't really matter what letter we use. We didn't even need to use X and Y. We could have used A and B, or whatever letters you wanted. So don't think too deeply about the fact that it's a Y versus an X. Okay, so that's our area function. So let's simplify this a little bit to make it easier to take the derivative. So we would get 2,400Y minus 2Y squared. So this is another example of one where you actually don't need to use calculus. If you wanted to, you could just find the vertex, because this is an upside down parabola, right? Like you have a negative y squared and then you have another part with y, so it's an upside down parabola. So you could answer this question by simply finding the vertex. But let's do calculus, because that's what class we're in. So to answer this with calculus, we basically just want to find the critical numbers of this function and then check whether, confirm that they're the right kind of critical numbers. So if we take the derivative of this function, we get 2,400 minus 4y. And so our we want to set this equal to 0 in order to find the critical numbers. So if we do that, we'll find that 2,400 is equal to 4y. I guess I kind of flip things around. Maybe let me just write it the other way, because I think it is a little more straightforward. 4y is equal to 2,400, and so that tells us that y is equal to 600. So that is our critical number. So now we can double check that that is actually a local maximum. And the way we do that is we take the second derivative and then we plug in our critical number. So if the first derivative was 2,400 minus 4y, the second derivative is just going to be negative 4. And so what does that tell us? That tells us that the graph that we're talking about of this area function is always concave down. And if it's always concave down, then the critical number we're finding is a local maximum. And if you were to plug in 600, you would get negative 4. So this is negative, and so that tells us that we have a local max at x is equal to 600. So the final step is to figure out what is it that the question is actually asking us for. So here it's asking us for the dimensions. So we need to figure out, we found just now what y is, we now need to figure out what x is. So the dimensions are y is equal to 600. So that's one dimension. And then how do we find x? Well, we know that x plus 2y has to equal 2,400. So we can just plug in 2 times 600 in for y and use that to find what what x is. So if we use again that fact that x plus 2y is equal to 600, that tells us, or sorry, is equal to 2400. That would give us x plus 1200 is equal to 2400, plugging in 600 for y. And then that tells us that x is equal to 1200. So the dimensions are y is equal to 600, x is equal to 1200. But again, just really pay attention to what the question's actually asking. And we'll actually look in a moment at one of the online homework questions that's kind of similar to this, but it would be very possible that the question actually asked you to find the maximum area. So if this question asked you for the maximum area, you would need to enter the area. So you'd need to multiply these two things together. So just pay attention to what the question is actually asking you for. So I just wanted to look, like I just said, at one of the online homework questions just to make sure everyone's clear on kind of like the picture that you should be drawing, because I think the way it's worded maybe isn't the very most clear. So let me just open a blank page here. So this is number, I think 19 and 20 are both sort of fence questions. Maybe I'll make this a little bigger. So let's look at number 20. So 20 says, a farmer is setting up separate pens for livestock by fencing off a rectangular area and setting up fences within the rectangle to create 7 parallel pens. So I just want to draw that picture for you in case you're having trouble picturing what that means. Basically what this means, so this is for number 19 and 20 on the online homework. And of course, I'm doing it for, like, as you are probably aware, your questions all vary slightly. So your question might say 5 parallel pens or 3 parallel pens or 2 parallel pens or whatever. So, make sure what I'm drawing is just for this specific example of 7 parallel pens. So pay attention to what your actual numbers are in your question. But so what would this look like? Well, we would have a rectangle, so some kind of rectangular pen. And then how would we get 7 parallel pens within this? Well, we would need to add 6 subdivisions, right? Because if we add just 1 subdivision, that gives us 2. If we add 2 subdivisions, that gives us 3, 4, 5, and I didn't make this quite big enough. So it would look something like this, right? 1, 2, 3, 4, 5. Oop, nope, I still didn't make it big enough. So it would look like this, right? So we'd have 1, 2, 3, 4, 5, 6, 7. But the important thing to realize when you're doing this question is that so let's say that you were supposed to do something related to the amount of fence that was used. So maybe if you did this similar to the other question that we just did, you would call this y, and then you would call like this whole distance x. If you were adding up the total amount of fence used, you would need to say x plus another x, right? Because in this case, you would have fence on both sides, so it would be 2x, and then you would have to add up like all of these different y's, right? Because you're using all of this fence. So it would be, in this case, 2x plus, and let's see, we have 1, 2, 3, 4, 5, 6, 7, 8y. However, when you find the area of this thing, it would just be x times y, right? Because the area is just the overall area. You don't need to worry about all these separate rectangles. So one other thing I just want to mention about that question on the online homework, or these two questions, is that they're very subtly different from each other. So the number 19 is very similar to the one that we just did because it tells you the total amount of fence that the farmer has, and then it asks you for the largest area. So that is going to be, the picture you'll draw will be different, but the kind of process will be similar to the one that we just did, except for that, again, it's not asking for dimensions, it's asking for area. The next question is kind of reversed. So in this case, you know the area, and you're trying to figure out what is the minimum amount of fence that you need. So I just wanted to draw your attention to that because you might look from one to the next and think it's like the same question, but there is a subtle difference. Okay, so we're going to do one more example of a question, optimization problem, and this one's kind of tricky, and on your worksheet, I'm going to put one question that's actually similar to those two I just showed you on the homework, and then I'm going to give you one question that is pretty tricky, kind of similar to the one that we're about to do. But yeah, I would say in general with these optimization problems, I'm not going to give you like one of the trickier ones on the final exam or anything like that. I'll keep it pretty simple, but just in case you're interested and motivated and want to kind of see more complicated examples, I want to make sure I show them to you. So this example, it has to do with constructing a box. So suppose you have 45 square meters of cardboard to build a box. So what is this box going to be like? We want it to be a box that has a square base and no lid. So maybe I'll just add that to this sentence here. So to build a box with a square base and an open top. So there's no lid, it's not like closed on the top. So the question is, find the dimensions of the box with the largest possible volume. So we want to see basically, given the amount of area of cardboard we have, what is the biggest box that we can build if that box is has a square base and an open top. So I already did a rough sketch of what this could look like because I didn't want to do it while the camera was rolling. So we have a square box, so maybe it doesn't look quite like that, but the base is square, the height may not be. So the way I drew it maybe that doesn't make it so clear, but basically what I'm saying here is that whatever the dimensions are of the, I'm trying to think what colors I want to use. I'll use purple here. So whatever the bases are, maybe we can call this X and this X. Because the base is square, those two dimensions are the same. However, the height is going to be potentially different. It could end up being the same, but that's not necessarily true. Now I don't know if this will make sense to anyone, but when you're looking at, if you look at this picture, you can kind of flip it so that it looks like it's going different ways. Sorry, I probably sound like I'm crazy. But if you stare at that box for long enough, your brain might be able to flip it, and it just happened to me and it was confusing. Anyway, okay, so let's go through the steps that we outlined in that previous question. So the first step we want to do is express in words, what is it that we're trying to maximize or minimize? So here we're trying to maximize the volume of the box. So the next step is to write down an equation that expresses the volume of the box. So how do you find the volume of a box or a rectangular solid? You do length times width times height, right? So in the same way that when you're finding the area of a rectangle, you do like length times width or base times height. In a three-dimensional object, you have to multiply all three dimensions. So the volume is going to be equal to, in this case, we have X and X, so those are just going to be, X times X. And then we have Y as our height. So we could also rewrite this as X squared times Y. Now, again, like in the last problem, this isn't really going to work for us because we need to make sure there's only one variable. So in this case, I think, well, let's see what we have to write down in order to do this. But we're going to do something kind of like in the last question where we're going to use the information that's given. So we're going to use the fact that we have 45 square meters of cardboard. We're going to use that to get rid of one of these two variables. So how do we kind of make use of the fact that we have 45 square meters of cardboard? Well, we need to add up all of the sides of this box And that is what's going to add up to 45. So if we look at the base, what's the area of that base? That's going to be x times x squared. And then we don't have to do anything for the top, right? The top of this box, like up here, that would also be x squared, but there is no top for this box. We don't need to worry about that. What else do we have? Well, we have this side here. So what would the area of that side be? Well, we know that this base here, or this length here, is x, and we know that this length here is y, so the area of that is x times y. And similarly, this is also x times y, right? And then this is also x times y. And so is this piece in the back. So all of the sides are x times y except for the base. So that means that we're going to have plus 4xy. And all together, oops, this picture looks kind of confusing now, but I'll just leave it. So if you add those two together, what should we get? Well, we should get 45, right? Because that's the total area that we have to work with for the box. So we could either solve this for x or for y. If we wanted to solve this for x, we would need to use a square root, and that's going to kind of make our lives more complicated. So let's solve this for y. So if we wanted to solve this for y, we could subtract the x squared from both sides, and then divide both sides by 4x. So y is going to be equal to 45 minus x squared over 4x. So now what can we do? Well, we can now replace y with what we just found here, and that will give us an equation for the volume that only has one variable in it. And so it's going to end up with only x's in it, right? So that means that it's going to be a function of x. So v of x is going to be equal to x squared times 45 minus x squared over 4x. And so we can simplify this. So we have an x down here and an x squared up here, so we can cancel those out. And so we'll be left with v of x is equal to 45x minus x cubed over 4. And so I'm gonna actually, maybe first I'll write it like that. And then I think to take the derivative, it will be simpler if we kind of split this into two fractions. But yeah, so basically we just kind of canceled out this extra x, and then we distributed the x into the fraction, into the numerator of the fraction. So nicest way to write this in terms of taking the derivative would be 45 over 4 times x minus 1/4 times x cubed. Okay, so our next step is to find the critical numbers. Now that we have the function that we're trying to minimize, we can find the critical numbers. So we want to set this function equal to 0. Or actually, sorry, we need to first take the derivative, right? So we have to take the derivative of this function, and then we'll set that equal to 0. So the derivative of 45 over 4 times x is just 45 over 4. And then the derivative of negative 1/4 x cubed is going to be negative 3/4 x squared. So now we can set this equal to 0. So let's actually multiply both sides of this equation by 4, because that way we can get rid of the fractions on the right-hand side, and it will just make our equation a little friendlier to solve. Okay, so now we can add 3x squared to both sides. And we can divide both sides by 3, and we actually could have done that in the last step as well. So if we divide both sides by 3, we get x squared is equal to 15. And then we can take the square root of both sides. And in this case, we don't need to say plus or minus, because we're talking about a real life object. So it doesn't make sense that one of the dimensions of the box would be negative. Okay, so that is one of the dimensions. So we now know basically the base. So we know that the base is square root of 15 by square root of 15, and now we just need to find the height. And so how can we find the height? Well, we have this equation here that says that y is equal to 45 minus x squared over 4x. So we can just put what we just found for x into that. So I'll write that down here again. So y was equal to 45 minus x squared over 4x. And so that tells us that in this case, y is equal to 45 minus square root of 15 squared over 4 times the square root of 15. And so that would be 45 minus 15, right? So that's 30 over 4 times the square root of 15. So those are our dimensions. We have, let's write all of them down, right? Because it's a three-dimensional object, so we should have 3 dimensions. So the dimensions are going to be square root of 15 by square root of 15 by 30 over 4 root 15. And I guess I should have put units on here. So our original units were square meters, right? And so that means that each of these dimensions has a unit of meters. So we have meters, meters, meters. And that's our final answer. All right, so that is it. And I hope you have a good weekend. And yeah, I hope you're all doing okay and hanging in there. And I will see you all next week.